In 1845, James Clerk Maxwell proposed that electric and magnetic fields interact to form a wave and mathematically proved it. The speed of the wave that Maxwell discovered was constant. From this theory, physicists deduced that, like water waves, electromagnetic waves needed a medium to propagate through, and they called this medium ether, which was assumed to permeate the entire universe. According to this theory, ether was considered necessary for the propagation of light. Just as sound waves need to travel through substances like air or water, it was assumed that light moved through ether. At this point, physicists began conducting experiments to understand the properties of ether and measure its speed. One of these experiments caused a major revolution in the scientific world. The Michelson-Morley Experiment, conducted at Case Western Reserve University in 1887 by Albert Michelson and Edward Morley. Now let's delve into what this experiment was and how it revolutionized science. Physicists in the 19th century believed that light required a medium, ether, to propagate through space. Just like sound waves, it was assumed that light needed a medium to propagate. Therefore, Michelson and Morley believed that as the Earth moved through this ether, a difference in the speed of light should be observed. The Earth revolves around the Sun at about 30 kilometers per second. It was assumed that this speed created an ether wind that would affect the speed of light. Imagine creating a wave in a river with a current. The speed of the wave is affected by the river's flow. Similarly, it was expected that the motion of light through ether would be influenced by the ether wind. Michelson and Morley designed an experiment to measure this effect. Let's explain this idea with a simpler metaphor. In a river flowing at a constant speed, if two swimmers start from the same point and swim at the same speed relative to river but in different directions, their times to reach the opposite shore would differ depending on the speed and direction of the river. The aim of this experiment was based on a similar idea: to understand the nature of ether by examining the movement of light in the presence of ether. However, Michelson and Morley encountered a problem. According to Maxwell's theory, the speed of light was very high, making it difficult to measure the time difference between two light beams with precision. To solve this problem, they aimed to create an interference pattern by having two light beams interfere with each other. This interference pattern would allow them to mathematically calculate the phase difference between the beams. Thus, they came up with the idea of using an interferometer to split a light beam into two beams moving at right angles to each other and reflect them back using mirrors to create interference. By looking at the phase differences, they hoped to find the same value predicted by the calculations based on the ether theory. Additionally, for simplicity, they aligned the experimental setup in a direction corresponding to the Earth's motion around the Sun. Let's now explore how this experimental setup worked. A laser source emits a monochromatic wave, i.e., a wave with a single wavelength. Let this wave propagate in the same direction as the ether. Then, this electromagnetic wave is split into two beams at right angles using a Michelson interferometer. The beams are reflected back using mirrors placed at equal distances and then interfere with each other. Let the distance between the interferometer and the mirrors be labeled W. The speed of the electromagnetic wave is denoted as an c, which is approximately 3 × 10⁸ meters per second. Let the speed of ether be denoted as v, and its direction be parallel to one of the two beams. Now, let's calculate the time taken by these two beams to travel along their respective paths before they interfere. First, let's calculate the time for the beam traveling parallel to the ether. As the beam moves towards the mirror, it moves against the ether wind, so the speed of light will be c minus v. The time taken is distance over speed, which gives w over c minus v. When the beam returns to the interferometer, its speed will be c plus v, so the return time is w over c plus v. Thus, the total time for this beam to complete its journey is this. Now for the second beam, which moves at an angle to the ether. If there were no ether, the speed of light towards the mirror would be c. But because of the ether, the horizontal component of the speed will be the same as the ether speed, while the vertical component is found using vector addition as the square root of c squared minus v squared. The total path for this beam is 2w, and the time to complete the journey is that. The time difference between the two beams is then Approximating for cases where the speed of light is much greater than the speed of ether, this approximation can be taken since ether can move at a maximum of the speed of light, and this function gives a valid approximation up to that point. We assume the speed of v to be the Earth's speed around the Sun, which we know, and the speed of light is also known. If we assume the distance w to be 1 meter, the time difference is approximately equal to 10 to the power of -17 seconds. Due to this time difference, the phase difference between these patterns is measured, and the experimental results are compared to the theoretical calculations. After performing the calculation, the experiment was conducted using a wave with a frequency corresponding to this time difference. In the experiment, a green-colored wave with a frequency around 5.0910 to the power of 14 Hz was used. The two waves will create an interference pattern. The phase difference between these patterns is measured, and the experimental results are compared to the theoretical calculations. Now that we understand the experiment, let's see what results were obtained and how they impacted science. When Michelson and Morley conducted their experiment, they did not observe the expected results. Although an interference pattern was observed, the phase difference between these patterns was much smaller than expected. In the paper published by Michelson and Morley, they explained this phase difference by showing a graph that compared the expected and experimental results. Thus, the results of the experiment provided no evidence for the existence of ether. As a result, many scientists of the time either considered the experiment flawed or suggested that the properties of the ether had been misunderstood. After this result, scientists like Lawrence and Fitzgerald did not immediately dismiss the existence of ether, but suggested that ether might not be affected by solid objects, or that the speed of ether or the Earth's velocity was incorrectly measured. However, in 1905, Albert Einstein introduced a new perspective with his famous paper on the electrodynamics of moving bodies. Einstein proposed that the speed of light is constant for all observers, regardless of their motion, and that light does not need a medium like ether to propagate. As a result, the Michelson-Morley experiment led to the abandonment of the ether theory and paved the way for the development of the theory of special relativity. The Michelson-Morley experiment revolutionized the scientific world and laid the foundation for Albert Einstein's theory of special relativity. This theory, which posited that the speed of light is constant and that time, mass, and length are not absolute, redefined the fundamental laws of nature. Einstein's work sparked a scientific revolution that would shape the future of physics. The results of this experiment not only opened up new pathways for physics, but also fundamentally changed the way we understand the universe. This journey would later open the door to other revolutions, such as general relativity,